Hello. In today's video we're going to start chapter 17. We're going to look at lecture 15, learning objectives 1 and 2. So we're going to look at the common ion effect and use the common ion effect for weak acids and weak bases, and then we're going to look at what a buffer is. So common ion effect basically tells us what happens when we add in something that has a common ion. So, or what happens to an equilibrium process when we add in a common ion. So, we kind of use the idea of Le Chatelier's principle, so this brings in Le Chatelier's. Where we basically take a system at equilibrium and we disturb it. Okay? So, the common ion effect itself, if we take two things, one is going to be an equilibrium process, and one is a one-way arrow. We add those two together. So we have something that has an equilibrium that produces ions, and then we have another thing, another process that is a one-way arrow that produces ions, and in both processes we have the same ion. Okay? So if we add a strong electrolyte, i.e. a soluble ionic compound, that contains the same ion as a weak electrolyte or insoluble ionic compound, the increase in ion concentration will cause a shift in the equilibrium. Okay, like I said, it's based on Le Chatelier's principle. So adding in that ion will shift your reaction away from that ion. Let's see what happens. Let's take a strong electrolyte, sodium fluoride. Sodium fluoride is considered a soluble salt. And then let's take a weak electrolyte, such as hydrofluoric acid. Okay, so we're going to take both of them and put them into the same solution. So first, when we add sodium fluoride into solution, it's going to completely dissociate to produce sodium ions and fluorine ions. Okay, so we're going to be producing as many fluoride ions as sodium fluoride that we put in there. So for every one molecule or compound or unit of sodium fluoride, we'll produce one ion of fluoride ions. And then our weak electrolyte, HF, this is a weak acid, so it's going to react with water. And when it does, it will produce H3O+, and fluoride ions. So both of these processes produce fluoride ions. Okay, so when we add this in, this sodium fluoride, we have a specific concentration of fluorine ions. Because of that, when it interacts with this equilibrium process, it will add in on the right side of the equilibrium process and cause a shift in this direction. So we will shift towards our reactants. So in the case of a weak acid or a weak base, this will decrease the amount of dissociation that we'll see. So, common ion effect in a weak acid or weak base will cause less dissociation of the acid or base. So it'll basically weaken that substance, will produce less hydronium or less hydroxide. So if we add a common ion into a weak acid, we will decrease our hydronium concentration produced, which will in turn increase our pH. If we add a common ion into a basic solution, or a weak base solution, we will decrease our dissociation of our weak base, and that will cause our hydroxide ion concentration to decrease, and when that decreases, our pH will actually go down. So if we add a common ion into a weak base, this will cause a decrease in dissociation, so hydroxide concentration, and therefore a decrease in pH. And like I said, it's going to be opposite with an acid. Acid will decrease our hydronium concentration, which will increase our pH. Okay. So, you can also see common ion effect when we look at things like a insoluble salt. So, insoluble salts will actually have some amount of solubility, and by adding in a common ion, we will actually cause precipitation. So, if we have the equilibrium process of lead chromate, this is considered an insoluble salt, but it does have some ions that dissolve. It's just considered insoluble because of how few ions it dissolves. So if we take and we add in something with a common ion, such as sodium chromate, that will completely dissociate it, produce sodium ions and chromate ions. We know that because all sodium salts are soluble. So this substance will add in here, which will cause a shift back towards our solid. So we can see in this picture, prior to adding the sodium chromate, we have less solid, and then after adding in the sodium chromate, we get a increase in the amount of solid that we produce. So it decreases. So our common ion effect decreases the molar solubility of insoluble ionic compounds. So those with equilibrium solubilities. So let's check how we're doing with the whole idea of common ions. So we've got F minus and pH. We want to calculate those for a solution that is 0.150 molar HF and 0.050 molar HCl. The Ka of HF is 6.8 times 10 to the negative 4. And from this information, we want to figure out what our pH and F minus concentrations are. So first, when we're attacking these problems, we want to look at our completely soluble or substance that's going to completely dissociate, so our strong electrolyte. In this case, it's HCl. HCl is a strong acid, so it's going to completely dissociate into chlorine ions and hydronium ions. So, we take our HCl, and it will completely dissolve to produce, and we're going to put some water, hydronium plus Cl minus. Okay, so for every mole of HCl we have, we're going to have the same amount of H3O plus produced. So let's just assume, for simplicity's sake, that we're in a 1 liter solution. So 1 liter solution. So in that 1 liter solution we have, we're doing a BCA table for this. We start out with 0.050 moles here, minus 0.050 plus 0.050 plus 0.050, giving us a total of 0.050 moles of hydronium and 0.050 moles of chloride ions. Okay. We can then take that, put it into our Rice table. So our weak electrolyte, HF, will react with water to produce hydronium as well, and our fluoride ion. So, care about water. We're going to put this back into 1 liter, so to give us a concentration of 0.050 molar. And we start out with 0.150 molar of our FHF. It's the equilibrium process, so minus X plus X plus X gives us 0.150 minus X, 0.050 plus X, and X. We can then put this into our Ka expression. So I'll put our hydronium, F minus, and HF concentrations in here, and put into it our Ka value as well, giving us 6.8 times 10 to the negative 4 is equal to X times by 0.050 plus X divided by 0.150 minus X. We have a Ka that's too large, so we can't do small approximation, so we need to do some math. So we multiply both sides by 0.150 minus X and combine, and we'll see that we get X squared plus 0.0507 X minus 1.02 times 10 to the negative 4 is equal to 0. Okay, so just mathing everything, putting everything on one side. We have an A, a B, and a C, so we can put this into our quadratic. Okay, and then when we solve for our quadratic, we get X values equal to 0.0019 and negative 0.0526, which we know is not correct because it's a negative value. So our x value is this one right here. From here, we can find our F minus concentration, which is equal to 0.0019 molar, and we can find out our hydronium concentration, which is 0.050 plus 0.0019, giving us basically 0.052 molar. And if we take the pH of that, we get a pH value equal to 1.28. Okay? So that would be a little bit higher than what we would get if we, or sorry, that F minus concentration is a little bit lower than what we would see if we did not have a common ion. Okay. We can see that if we go about looking at no HCl being added. So if we want to just calculate the F minus concentration in a 0.15 molar HF, then it would look a little different, right? Because we wouldn't have HCl added. So if we were to do that math, we'd start out with 0.150 molar there, and we'd start out with nothing over here, minus x plus x plus x. Put this into our equation. 6.8 times 10 to the negative 4 is equal to x squared divided by 0.150 minus x. When we multiply across and combine, we get x squared plus 6.8 times 10 to the negative 4x minus 1.02 times 10 to the negative 4 is equal to 0. Put all of this into our quadratic. We would get x value equal to 0.0098 or negative 0.0104, which was not correct, so we get this x value. And then we put it in, we get F minus concentration equal to 0.0098 and a hydronium concentration of 0.0098. If we compare, we see that our F minus concentration is significantly smaller when we add the Cl minus in. But if you notice, our hydronium concentration is larger. And that should make sense because we added in HCl, right? So the product on the right side, the product of multiplying the concentrations on the right side should still be equivalent when we're comparing the two. We just, because we didn't add in, because we didn't include acid in at the beginning, our hydronium concentration is a little bit smaller, so we'd actually see a pH that is a little bit higher. And I wanted to show you guys this because I said on here that, that if we add in a common ion to a weak acid, we would decrease the dissociation, which means we would produce less hydronium, which means we would have a higher pH with a common ion, which is not what we see here, but we have to remember that the amount of hydronium we produced has decreased. For our HF, we just added in a significant amount of hydronium by having a acid added in. So in general, if you add in a common ion to a weak acid, it will decrease your hydronium, which will then increase your pH. But that is not going to be true if the common ion you add in is hydronium. Okay. Moving on, let's look at buffers. So buffers are a solution that contains a weak acid and its conjugate base, or a weak base and its conjugate acid. So the weak acid and weak base are both going to have a common ion. And what's nice about a buffer is, or the reason that buffers are important, is because they will resist large changes in pH when small amounts of strong acid or strong base are added. So keep in mind that if you add a strong acid or strong base, you're going to directly produce hydronium or hydroxide, which significantly changes your pH. So if you add a strong acid or strong base into water, it will completely dissociate. Now, that's a little bit different when we add a strong acid or a strong base into a buffer. So if we have a buffer, such as a sodium or a acetate, acetic acid sodium acetate buffer, which is a fairly common buffer. If we take this buffer and we add in anything to this acid or base, our buffer will come and neutralize that. So for our addition of base, it will react with our acid, producing sodium acetate and water. If we add acid into this, it'll react with our base, sodium acetate, to produce acetic acid and water. So instead of just adding in a base or an acid, which will completely dissociate to produce hydronium and hydroxide, we're now just increasing our sodium acetate or acetic acid concentration, which are already part of our buffer solution. So very little changes in pH will occur. When we want to calculate the pH of a buffer, we're going to use a specific type of equation, which is based on Ka's and Kb's. So for our acid, remember that our Ka is equal to our base concentration times by hydronium, specifically its conjugate base, over the acid concentration. Okay? We can rewrite this as H3O plus concentration is equal to Ka times by acid concentration over base concentration. For the base, our Kb is going to be equal to the conjugate acid concentration times by hydroxide over our base concentration. And again, rearranging, we get hydroxide concentration is equal to Kb base over acid. So we can then take either one of these, our hydronium concentration being equal to our Ka acid over base, and we could take the log of both sides, and log of hydronium gives us pH, so we get pH is equal to negative log Ka acid over base. Right? So the log of Ka, or if we separate this out, we get negative log Ka minus log acid over base, and the negative log of Ka is pKa. And we can change that to a plus. So we change this to plus by flipping our base and our acid, and we get pH is equal to pKa plus log acid, or sorry, log base over acid, which is our Henderson-Hasselbalch. We can also do the same thing with our base, and what we get is POH is equal to pKb plus log acid over base. Okay, so this gives us our Henderson-Hasselbalch. Some notes about our Henderson-Hasselbalch. So we have our two forms. pH is equal to pKa plus log base over acid. And it's our conjugate base and our acid concentration, or if we're looking at POH, pKb plus log conjugate acid over base. There are some limitations to this equation. We have to, one, have a buffer solution. So for it to be a buffer solution, we have to have a ratio of acid to base bigger than 0.1 or less than 10. So basically, our base or acid can only be 10 times the size of the other. And then we are assuming X is small. So if that is not a valid assumption, we can't use Henderson-Hasselbalch. So if we have a Ka or Kb that is 1.0 times 10 to the negative 4 or greater, then we can't use our Henderson-Hasselbalch, because we would say that our X is small approximation is not valid. Okay, let's try. We want to determine what our pH of a buffer solution is that uses acetic acid with a acid-base ratio 2 to 1. So we have acid to base ratio equal to 2 over 1. And we want to determine its pH if we're using acetic acid, which has a Ka equal to 1.8 times 10 to the negative 5. So the first thing we want to do is we want to solve for our pKa, which is negative log Ka. And when we solve for that, we get a value of 4.74. And then we can put this into our equation. pH is equal to pKa plus log base over acid. So pH is equal to 4.74 plus log 1 over 2, which gives us a value of 4.44. As a note, you can also do the common ion effect with this, and it would work the same way. Just a lot more math. Okay. Let's try. Okay. That is it for this video. And we'll continue with Learning Objective 3 in a further video. See you guys later. Bye.